Hello, this is Jennifer Dassinger with A Plus College Ready, and I hope you were able to practice your empirical formula, the simple version of the compound, versus the molecular formula, which is the true version of the compound. Now, we're about to cover hydrates. And hydrates, if you remember from our ionic compound notes, are ionic compounds that have water loosely bonded to its structure. Remember, it absorbs a certain amount of water from our atmosphere, and that's particularly important for us here in the South because we've got to remove that water due to the humidity. Just another thing to remind you about is that dot means to add, not to multiply in your math class, but it is to add in science. Sorry for that. I don't make the rules, we just follow them. So to add the mass of all the waters to the mass of the anhydrous, and anhydrous, of course, means without water. So in the example that I've given you is the sodium carbonate. So with all the 10 waters taken off, that would just be the anhydrous salt. But the natural salt that you'll just pick up in nature or from your shelf is realistically the sodium carbonate decahydrate, for that 10 meaning deca. So let's go through an example of calculations with hydrates. When trying to solve for the amount of water, you're gonna have to use the empirical formula method and percent composition. So if you haven't practiced those and are not comfortable with empirical formula percent composition, I would pause this video, go back, practice, rework some of those problems before proceeding. Okay, so let's take a stab at it. What percent of water is found in barium chloride dihydrate? There's 2 waters added. So think about it as 2 parts. Look at your anhydrous salt first, the barium and the chlorine. Use your empirical formula steps. I've got 1 barium. I multiply it by its atomic mass from the periodic table. Therefore, I get it's 137.33, just like it is on the periodic table. Chlorine. I take the subscript of 2, that means there are 2 moles of chlorine, and I have to multiply that by its molar mass, remember, from the periodic table of 35.45 to get the 70.90 grams of moles per 1 mole of chlorine. Now, I have to add those 2 values together of my anhydrous salt to get my 208.23 grams in 1 mole of just the barium chloride side. Now, for my dihydrate, 2 moles of water. Now, what I've done is I've kind of shortened down some steps, and I've already plugged in the 18.01 molar mass of water. I kind of recommend you memorize that. It just cuts down on some steps for you and makes your life a little easier. So instead of calculating the 2 hydrogen times the 1.01 plus the 16 to get my 18 value, I just kind of did that for you. So when I take the 2 times the 18.01, I'll get my 36.02 grams of my per 1 mole of my water. But then to get a total amount, I'm going to have to add both parts together, my anhydrous side and my water side, to give me my total hydrated salt molar mass of 244.25 grams per mole. Now, I just did my empirical formula method to find the masses of each. Now I can plug it into my percent composition equation to solve for my percentage of water. Remember, percent composition is essentially part over the whole. I just want to know my water, so I'm going to take the molar mass of my water of my 36.02, use it as my numerator, and divide that by the molar mass of the entire hydrated substance of the barium chloride dihydrate, which is the 244.25 grams per mole. My units cancel of grams per mole. I multiply by 100, and that, of course, give me my percentage of the 14.75% of water in this substance. And as you see on the right, there is an actual picture of what it would look like in your chemical storage cabinet. Let's look at another calculation of using hydrates. Find the percent of water when the masses are given. So this is a little different type of problem. In the first problem, a 5-gram sample of a hydrate, sodium carbonate, was heated, and only 1.85 grams of the anhydrate remains. Remember I talked about earlier that you're going to do this empirical formula lab of a hydrate? Well, this is what you're doing in lab. You're going to be given this salt, the hydrated salt. You don't know how much water is there, but assuming you did the experiment correctly, you removed the amount of water through heating. So essentially, you have the 5 grams to begin with, but in the end, after heating it repeatedly in a constant method, you'll get only 1.85 grams of the salt anhydrous, remember, salt left. Therefore, that means I have to subtract, and the amount of water that was removed was the 3.15 grams of water. Well, this is pretty simple because all I've got to do is take my grams of my water that I burned off into water vapor, changed it into water vapor, divided by the total gram sample, and I got that I removed 63% of that compound's mass was water. So a lot more water vapor in the air. The second kind of problem that you're going to see is to solve for the N, or ratio of waters attached to the anhydrous salt. So again, look at the question. A 3-gram sample of a hydrate of zinc sulfate, we don't know how much water is attached, is heated to a constant mass of 1.68 grams. So again, we've heated it in lab, we removed the water as best as we could at a constant heating method, and only the anhydrate remains. So now what's the value of N? Well, just like you did in the previous problem, you're going to take your entire gram sample of the 3 grams, you're going to subtract the anhydrate mass that was left behind, or which was remaining, to get the grams of water that was converted into vapor of the 1.32 grams of water. Now I have to take my grams of my water, divide it by its molar mass of water to get my moles of water. Then I'll take my grams of the zinc sulfate, divide it by its molar mass of just the zinc sulfate. So I did a molar mass calculation there of those two to calculate those, of the 161.44. Then I got my moles of my zinc sulfate. Just like you did in an empirical formula, you now have to look at the least mole amount, which is of course my zinc, and I will divide my moles of my zinc by itself to get a ratio of 1, of course, and then I will take my moles of my water and divide it by the moles of my zinc, and that will give me a value of 7. So now the answer is zinc sulfate. Now again, that little dot is missing on the PowerPoint there, I see, added to 7 waters, and it's called zinc sulfate heptahydrate. Hope these calculations helped. If you, these are the same examples that are in the student notes, so if you'd like to refer back to the student notes, these are the exact same ones that I have there for you. These are the type of problems that you'll usually see when in lab removing water from a salt. So hope you stay hydrated and get to practice. Good luck.